Right, second half of exponential growth decay notes. Oops. On April 26, 1986, the number 4 reactor at the nuclear power plant in Chernobyl, Ukraine exploded, releasing over 100 radioactive elements into the atmosphere. Most of these elements were short-lived and decayed quickly. One of the most dangerous of these elements was cesium-137, which has a half-life of 30 years. Write the exponential decay model. So that gives the number of grams remaining after T years if a 2,000 gram sample was originally released. So exponential decay model means we're going to have a negative in our exponent. If it didn't say decay model, the key up there is that half-life. All right, so P of T equals, it says we started with, I believe it was 2,000 grams. So 2,000 E to the negative, and then it's KT, where K is the natural log of 2 over, in this case, because it's decay, the half-life. And if we read over here, the half-life was given as 30 years. So there's our K. So natural log of 2 over 30, and we're going to leave just as is. Nope, not 2. ln of 2 over 30 T. Just make sure that T is not in the exponent. All right, so T is our time, and our units here are years. P of T is our amount, and our units given were grams. So always know your units. All right. Part B, use the model from Part A to determine how much is remaining after 35 years. So after 35 years is telling us that T equals 35. So we're plugging in 35 for T. All right. P of 35. We've got 2,000. E to the negative natural log of 2 divided by 30 times 35. Typed into our calculator very, very carefully. Use your fraction template as needed. And that gives us 890.3, no, 0.898. And then we go read, round to 3 decimals. So you always want to know how to round so you don't get it wrong. 890 point, it's 8, 9, and then it's 8.7, so that 7's going to bump it up to a 9 grams. All right. Next, if 20 grams is considered a safe amount, use the model from Part A, again, issues with letters here, to determine how many years it takes for the amount of cesium remaining to be considered safe. All right, 20 grams. Grams is our P of T unit, so this time we're given P of T is 20, and we are looking for the time. So we have 20 equals 2,000 E to the negative natural log of 2 over 30, no, times 35 times T. 35 is the last problem. All right, from there, remember exponential equations get the exponential term by itself, so we're going to divide both sides by 2,000. So we have, when we divide, it is a nice, pretty decimal. So it's kind of your choice, fraction or decimal here. Since the decimal's pretty, I'm going to use it. E negative ln 2 over 30 times T. Once the exponential term's by itself, natural log both sides. That is going to give us the natural log of 0.01, whatever that number is. Remember, natural log of E is the exponent, so negative ln 2 divided by 30 times T. And at this point, either divide or multiply by the reciprocal, completely up to you. Just be careful if you're going to choose the division, because you got to type it in correctly. So you got a little baby bar in the bottom. So we're going to get T is, we've got the natural log of 0.01 divided by negative ln2 over 30. So just you got to make sure you get this thing typed in right. So we do some very, very careful typing with some nested fractions, and the calculator spits out 199.315-ish, and then we go reread. Round to the nearest year, so the 0.3 is going to hold it at 199 years. That was a long time. All right, so there's your part B. Try to get the whole problem up here. There we go. Barely. All right, next. Logistic growth model. A logistic growth model is a special type of exponential growth model, and it's when there's a population cap and you cannot exceed that population. So here's just a real rough graph of what a logistic model looks like. So the function begins to increase exponentially. It's usually for like diseases. COVID actually follows a logistic model. There's lots of articles on it. It increases exponentially, and at some point in that population, the rate at which it's spreading begins to slow because it's running out of people to infect, and it begins to level itself off. Now that leveling off right here is due to a horizontal asymptote at what's called y equals L. And L, if you look at that formula, is this numerator value. That is the population size. You cannot infect 1,500 people if there's only 1,000 total. Right, so here's an example that actually did happen. In 2009, a large outbreak of the swine flu caused schools area-wide to close their doors. Assume the swine flu spreads across a particular college campus according to the logistic model given, where S of T is the number of students who have been infected T days, and after T days, and T equals 0 is the day the flu first begins to spread. It's a mouthful. So just kind of as a note, that number right there is our population. So this college campus has a population of 2,200 students. All right. How many students were initially infected? So in there it does say T equals 0. It's not always going to say T equals 0. You do want to remember initially corresponds to when time is 0. So we're plugging in 0 for T. So we've got our 2,200 over 1 plus, and I know it was 999 and then something, e to the negative 0.01 times 0. And then again, very, very carefully to your calculator, use your fraction template as needed, and the calculator spits out 2.2. Nice, pretty-ish. Answer to the nearest student. So again, we're not going to infect parts of students. We infect whole students. 2 people or students. All right, B. How many were infected after 4 days? 4 days, unit of time. So when T is 4. So now we're doing S of 4. 2,200 over 1 plus 999 e negative 0.1. This time times 4. And from our handy dandy little calculator, we get 3.280. Go reread. Answer to the nearest student, 3.2 would be 3 students. All right, part C. Using this model, do you think the entire population will ever be infected? So that's going back to this graph here. This is the question that never changes. This answer doesn't change. So if we look at this graph, if you notice that population is leveling off, or that the function is leveling off at the population value, because of a horizontal asymptote, this type of function never crosses its horizontal asymptote. So what that translates to is the entire population is never infected. So like COVID, there was always that one person who was never infected. COVID does follow a logistic model. You can research some of those articles. So we're going to say no. And the reasoning, the because, it's my lazy shorthand because, there is a horizontal asymptote, which I'm going to call a HA for short, at y equals 2200, which is the population value. It never infects an entire population. All right, part D. After how many days is the flu spreading at the fastest rate? How many days means we are looking for T, so that means we have to have a number of students. And the key here is going to be that fastest rate. So what you want to know about the fastest rate is this occurs at the T, or I guess we're looking for T. This occurs when the Y value, or S of T, is half the population. The fastest rate is at half, or the midpoint, of your population value every single time. So our population was 2,200. So we take our population 2,200 and we cut it in half by dividing by 2. So our fastest growth rate is going to be when 1,100 students were infected. So algebraically, we've got 1,100 equals 2,200 over 1 plus 999 e to the negative 0.1 t. All right, so algebraically here, what has to happen is we've got to get that lovely denominator out. So that in order to get it out, you could do a little crisscross applesauce. You can cross multiply, whatever you'd like to do, and which essentially means we're just going to multiply on both sides. So if you want to do your little crisscross, it's essentially like we are putting this 1,100 over 1, cross multiplying, and we are getting 1,100 times that denominator because it's coming to this other side. So we're clearing our denominator. And then we still have the 2,200 on the other side. So now it's no more fraction. All right, at this point, I want to just get rid of that 1,100. I don't even want to try to distribute with all that mess going on. So we're just going to divide it off. Left side is going to be this wonderful set of stuff with now the 1,100 gone. And then we divide and we get 2. So then we move our 1 over. So 999 e to the negative 0.1 t equals 1. We divide to get the exponential term completely by itself. The division bar is a little crooked. Oh well. All right, this fraction is not a pretty decimal, so let's leave it alone. Once the exponential term's by itself, we take the natural log of each side. All right, and then that is just the exponent. 0.1t equals the natural log of 1 over 999. I'm out of room, so I'm going to come up here. We're going to go this direction. Maybe. Come on. iPad, arrow. There we go. I'm going to copy it, negative 0.1 equals natural log 1 over 999. Divide to get t by itself. So t is the natural log of 1 over 999 all over negative, that's terrible, negative 0.1. So if you want, you could nest that in parentheses. And then we calculator it. So we have typed very carefully, use your fraction templates as needed. 69.067 and some change. Reread. Answer to the nearest day. That would be 69 days. So a little more algebra involved, but the nice thing is these steps are very repetitive with each of these types. Let me see if I can get this whole problem up there. It's gonna be tiny, but there it is. All right, the rest are you try it, so feel free to try those and check them with the key.